All right, y'all. So, first of all, if you are watching this video because you were one of my folks that was gone at collage practice, I hope you had fun. I loved being in collage when I was in high school, so I hope that you guys really enjoyed your time. If you're watching this video just to kind of get a refresher on this content, that's also awesome. We're glad you're with us. I don't know how to do this without sounding like a very cheesy 2000s influencer, and I'm not sorry about that. What I do know how to do without sounding really cheesy is question number 16. So, for those of us that were gone the day that we finished up 7, we are looking at 16 through 20. Okay. So, this energy diagram for the equation in 12 above, that is that same equation that we've been looking at all unit. And you would think that at some point I would get faster at writing it, but it never happens. There's our neutrons. Sorry, they had to kind of sit below. All right. So with number 16, we are drawing an energy diagram. So that's not a graph, that's a diagram, which I know they're really similar. A graph, though, has numbers on it, and this is not going to have a graph on it. Okay, this is not going to have numbers. So start by kind of drawing out my shape. Where here's the energy. Down here is either the reaction progress or the time. I like to put time because it's easier to fit. But I would take reaction progress there. Sorry, wow, I'm making a huge mess on the screen. All right. So from here, we're going to add in our labels for high energy and low energy and more and less stable. So for our energy here, we can tell that you have a higher point and a lower point. Label your energy according to that. So you have high energy here on the top and low energy on the bottom. All right. And then kind of think back to our kindergartner example. We talked about how high energy kindergartners are not stable people. This is going to be less stable. And our low energy storytime kindergartner is a more stable, predictable person. So we're going to put our, I almost just write storytime there. That was incorrect. This is our more stable person, okay? This is somebody who's a little more zen. They have low energy. All right, it's our kindergartner example. So from here, we have to look at 12 and decide, is this endo or exothermic? And we have spent a long time with this equation, right? We've spent a whole unit looking at just this equation. So I'm hoping that you recognize this to be an exothermic equation. If it's exothermic, the energy is going to decrease over time. So I like to draw, like, here's our reactants, and then they undergo some sort of a change, and then the products. Okay. This right here is the point where I start to lose people. This is where we've had the most mistakes in the past, and I'm hoping that by just kind of going over this repeatedly in class that we will really see some success. So the next step is not to try to graph any points. Don't graph any points on this axis. You don't even have numbers to graph them off of. Okay, all we can do is label our reactants and products. So I'm going to put our reactants up here. And our reactants were that neutron and U-235. So those are my reactants. For the product, that's R for reactant and then P for product. That's going to be your krypton 91 plus barium 142 plus 3 neutrons. And I will try to zoom in on this. I'm really sincerely hoping that the grittiness that I'm seeing on the screen as I'm doing this is my computer and not my camera, because I would not like it to be that gritty for you all, but if it is, you'll still definitely be able to tell what I'm doing here. Okay, so I zoomed in just to make it a little easier to see. All right, so from here we took a look at 17. And so I know that we did some practice in class with the hydrogen helium questions, and then we talked about barium and krypton, and then we looked at iron. What I would really like to point out is that this is a fusion section. So the reaction that's happening with uranium-235 is a fission reaction. Remember, in fission, we're having these elements come out of one nucleus into many nuclei, right? In fusion, the reverse is happening. You're having two or more nuclei combine into one nucleus, singular, okay? So for 17A, go ahead and notice the points on the graph where we find hydrogen and helium. Take a moment, notice them, appreciate them, pay them a compliment, whatever makes you happy. But there's nothing you actually have to do. For B, we're looking at the model of this reaction, which is kind of interesting to take a peek at. In a fusion reaction where hydrogen fuses into helium, see the model below, is the binding energy increasing or decreasing? So we're going to look on our graph here, and we see that the energy for helium is way down here where it's more negative. So this is going to happen because it's energetically favorable, right? The binding energy is going to decrease, and things in nature are going to tend to move to a less energetic state. So we have a decrease in our energy here. When we have a decrease in energy, where does that energy go? Okay. We've talked about where it goes when it's converted, but in this situation, energy is not necessarily being converted. Some of it is also being released in this situation. If we are releasing energy, is this endo or exothermic? This one is going to be exothermic because we're releasing. Okay. So draw an energy graph showing the energy of the reactants and products from the balanced equation in 17b above. This, folks, is the balanced equation. There's your arrow. All right, so we're going to include labels for high energy, low energy, more stable, and less stable. What I would like you to do is actually pause the video in just a second here. I want you to build just the framework. So you're going to build the L-shaped chart, and you're going to put the labels for high and low energy and more and less stable in, okay? So go ahead and pause the video now. All right. So it was a quick little pause there. I went ahead and drew in our bracket. So again, E for energy, and then time on the bottom, high energy on the top, low energy on the bottom, and then we have these blanks for stability. So remember, more stable stuff is going to be low energy. If we think about the soccer example that we have used in class before, that ball at the bottom of the hill, when it's really stable, is really low energy, right? It's not moving at all. Okay. So high energy is going to be low stability. Low energy is going to, let's just put more. Let's go with high stability. Okay. So going from here, we're going to draw in our line. So we looked and saw that this is exothermic, and I want to get some stuff real quick cleared up. Not every reaction is exothermic. Okay. This is something that has been a very common falsehood, is that every single reaction ever is exothermic, and that's not true. If you've ever used one of the instant cold packs, those actually are an endothermic reaction. You've ever used a can of any kind of aerosol, you know how they get cold? That's why they're endothermic, right? The other thing that I want to kind of continue on with that is that when we're looking at fission and fusion, they're going to behave the same way, and that's not true either. Okay, so even though in this instance they did both come up with an exothermic reaction, they're not always going to behave the same way, and I want to make sure that we have that down. Okay. So for our exothermic reaction, I'm going to draw my reactant, stable, change in energy, my products. Okay. And then I'm just going to go in and label. Again, we're not labeling here. This curve should not have any writing. None. Don't write on it. Up here, though, we're going to have reactants. So I put my little label R. And our reactants are 4 hydrogens. Folks, this is specifically the reaction that is occurring in our sun. So, if anything gives you a good hint, this is what's going on in the sun, the main source of our energy, right? It's where we get all of our light and heat from. That happens when hydrogen fuses, releases energy, and turns into our product, which I'm going to pull from up here. Our product is a helium-4 atom. In this instance, we would not write it as an alpha particle. Okay, we would write it as a helium-4. We're only going to write it as an alpha particle when we're specifically looking at scenarios in which decay is occurring. Okay? So in this instance, even though helium-4 is an alpha particle, we're not going to write it as an alpha particle. We're going to write it as a helium-4. All right. So I hope that this kind of helps to go over these 2 energy graphs or energy diagrams. There's something that we're definitely going to continue to see as we move through this class. And the more chemistry we do, the more we diagram energy. So if you love doing these, you are in luck. If you don't love doing these, you're going to learn to love it by the end of class. The answers to number 19 and number 20 are posted already for you on the week 20 Google Slides. Or not week 20. Wow, week 15. There we go. It feels like week 20. They're posted on the week 15 Google Slides. All right. If you want to try to answer them, and I would prefer that you do, let me give you a couple hints here. For number 19, the binding energies help us to explain why fission or fusion is going to make something more stable. Keep in mind, elements are moving towards a lower energy state. And then for 20, how does the mass loss in fission eventually end up as electricity? That one's going to require a little bit of thinking. I think I answered it in 4 or 5 bullet pointed steps on Google Classroom. If you have questions about anything I went over, if you want to go over this lesson again, anything like that, please don't hesitate to reach out. Let me know. I will make sure that happens for you. Especially with these graphs, like I said, we're going to see them quite a bit. So I want to make sure we're all feeling really comfortable as we move towards the end of our semester. All right, folks. If you have questions, like I said, don't hesitate, reach out. But that's all for today.